So in this chapter, we will discuss about the message passing architectures, which includes the methods of communication and the movement of data among multiprocessors. So this is typically done by sending and receiving the commands and the pair of commands which must be written into the application by a programmer. So the programmer are going to write those sending and receiving the messages. They initially initiate a method by which they can send a message, and then they start receiving those messages in response to like similar finding the finding the address of google.com. So you want to access the page, you just find Google, and then Google return it by its IP, and the page which is stored over on which is listed with the name of the Google as the index page, it returns back to you, which is actually a search engine page, which is a tab to search and then search further and so on, all those things. So these system eventually gave you a weight of internet connected uh, path by which the, such message passing protocols and message passing things are to be implemented in the message passing systems over the internet. So how to let me first introduce that what we are going to study in this chapter. So in this chapter, we will discuss different aspects of message passing, including a programmer model, and then message routing, network switching, processor support for the message passing, and examples of the message passing systems. So if we look towards the message passing, a message passing architecture is used to communicate data among different set of processors with the need in the global memory without the need for global memory. It's not with. If it is with, then it's a shared cache architecture. If it is not shared memory architecture, so it must be uh, a message passing architecture. So the basis of the scheme is that each processor has its own local memory and communicate with other processors using the message to that process is used to eliminate the need of a large global memory, and they are overcoming the requirement of a global memory altogether. So in the figure 5.1 shows the main component of a message passing multiprocessor architecture. There are n nodes in the figure numbered n1 to nn. A node n1 consists of a processor pi, which is actually a chain of the number of processes which has a local memory m of j. So when we notate p of I, so p of I means p1, p2, p3, and p4. So m of I is actually p m1 of the p1, m2 of the p2, m3 of the p3. So there is no such interconnection among them, like m2 is connected with p1. That's not a possible case. So each processor has its own address space, no communication with each other by a link called the external channels. And via the interconnection network, normally a static type of network, like you do not need to have a multiple sort of an IP communication, like you do not have a dynamic IP. So if the IPs and interconnection networks are dynamic, it is very hard to know that which memory has passed this message. Like you have to remain the same with your uh, network type. If I'm connected with your network through this blackboard or through any other medium, so in this case we have to be static IP till the time this session works. If we continuously change this IP, we might find that there are something uh, in the network that changes its state, like similar like a mosquito flying in the air. So if it is changing the continuous state, you might not get the exact location of that. So a message actually passed towards that node might not lead to another to the destination point, but it might be dislocated or to go towards another node, which is actually not the required node. So in particular, the hypercubes and the nearest neighbor two-dimensional and three-dimensional mesh interconnections are to be used we will discuss it with a figure. So, but initially we will look towards the figure, which is actually the 5.1 figure. And this message passing system brings an interconnection networks among different number of the processor which has their local memories. As I said, P1 is related to M1, and then P2 is related to M2, and similarly like the Pi is related to the P M of I, and P of N is related to the M of M. So there is a clarity should be generated over here, that we might not write M of N and P of N in an example. So over here we cannot say that P of 0 and M of 0. So we normally write P of I and M of I. And if we submitate or use a summation sign with it, we can say, okay, P sum of P, where P starts from I to the number of N. And similarly, the number of processors, if we sum all together, we can say, if we sum all the number of memories all together, we can say sum of M, where M starts from I and still N. So there is also one thing we need to consider, and that is the designing a message passing interconnection network using a link bandwidth and a network latency. So these two things actually create some considerable issues and attention for those who wants to develop such things. So the link bandwidth is defined as the number of the bits that can be transmitted per unit, bits per second, and then network latency is defined as the time to complete a message transferred through the network. More or less, in other words, we can say that if number of the processor is larger than the number of the processors, so if we have more number of processes that we need to process with the number of the processor, then more than one process will have to be assigned or executed on a processor in a timeshare fashion. Like you have 10 processes and you have two processors working together. So every processor has 5 processes shared in a time-based manner. So there is one more thing you need to remember, that the processes running on a given processor use what is called the internal channels to exchange the message among themselves. So they actually use a method which is called as an internal channels. By this method, you can simply what you can do, you will have to be executed in a time shared manner. Process running on a given processor use a called time internal channels, and that internal channels are actually the buses which are linking the two processors all together using an interconnection network. So they can send and receive a message. An important advantage of this form of data exchange is the elimination of the need of synchronization construct. So there is no arbiter required, there is no synchronization of the buses required. So every time you need to execute something, you have your own processes, and then you in your own processor, and based upon your own process and processor, what you need to do is you execute something and then inform others that okay, I did that. So in the figure 5.2 shows an example of the message passing system consisting of 4 processes. Let us see the figure 5.2. This is the figure 5.2. So every time the outside word is connected towards the processor P3, over here it is returning the output. But however, the P1, P2, and P4 are interconnected towards in a message passing manner. That every time P1 is passing message to P2, and then P2 is message then there is a message from outside world which is actually an input from an IO coming to the P3, and then P3 passes a message to the before. So it actually remains things in its own hand. So there are types of the granularity, but before the granularity, we come to know that what actually is a process granularity. So process granularity is the size of a process in a message passing system can be described by a parameter called the process granularity. So how much it is granule, every time when you look towards, if it is less granule, so it means that it needs more computation time than its communication time. The numerator must be higher than the denominator. So every time if you're getting a higher number of the process granularity, it simply depends upon the computation time. So the process is big, it takes much computation time, so the communication time is lacking behind it, so it creates actually the higher number of the process granularity. However, if we look towards the types of the process granularity, we look towards many things. That is simply, we can see that there are three major types, which is a coarse granularity, medium granularity, and the fine granularity. The question arises over here is, how do we comes to know that what type of granularity is occurring, or how we can distinguish it? So we are learning here that if we have a coarse granularity, then each process hold a large number of the sequential instructions and take a substantial amount of time to execute. So if we coarse granularity, we are talking about, we have number of processors, we have number of threads among the processors, and we have the memory, and they are all sequentially aligned all together. If we have a medium granularity, then since the process communication overhead increases as the granularity decreases, medium granularity describes a middle ground where communication overhead is reduced. Like simple, number of the processes are lesser than the coarse granularity, and there is an improved communication channel. So we can say, okay, there is a likely a chance that processors get their message received on time. So if we are talking about the fine granularity, so in this case, each process contains a few sequential instructions, as a few are just one instructions. So few instructions or small thread number of the threads, which are actually division. A thread is actually a division of the uh, of an instruction of a program. So if you are looking towards such a kind of a thing, by which if you are going to achieve a fine granularity, then in this case you have a few sequential instructions, not a large and not a middle, or just you have a less number of instructions, and then you will achieve a fine granularity. So what you need to do, if you have a coarse granularity, you will adopt those channels or those programming methods by which actually you can achieve a medium or a fine granularity. So every time when a framework is introduced, or some method is introduced, or some algorithm is introduced, or some language is introduced, they are actually looking towards processing things on a fine granularity. That means that a processor might not get so much load that it's overheated or burnt or create some issues or shutdowns whatsoever with the thing. So if we look towards the routing in a message passing network, that's absolutely the thing. Then every time you are passing a message, you must need to know that what is the routing method by which you can route a message from processor P1 to the processor Pn. You understand my point? So in this way, you are categorizing thing that if a processor wants to send a message, so the message should deliver to the known node or the destination node, which is actually marked as the destination. So there must be something called as a routing. You have already read this and study this routing protocols and all those things in a computer networks and communication. But over here, we are looking towards a routing is defined as a technique used for the message to select a path over the network channels. So formally speaking, routing involves the identification of a set of permissible paths that may be used by a message to reach its destination. So they are looking towards the permissible path. I will highlight all those things. Permissible paths that may be used by a message to reach its destination, and a function of n that select one path from the set of permissible paths. So there must be a function which we call as an n, and that n function is used to select one path from the number of the path and the permissible path available. So a routing technique is said to be adaptive. If a given source and destination pair, the path taken to the message depends on a network condition, such a network congestion. If there is a congestion and they can select another path or trying to have another path to reach the message from origin to the destination, then it's called to be as an adaptive. So contrary to the adaptive routing, there is a deterministic routing technique also called the oblivious, which determines the path using only the source and the destination regardless of the network conditions. That whatever be the conditions, you know that there are some people that if there is some congestion occurring on a road and on a traffic road, real life, and there is some congestion on the road, they actually change their path and they find a new path to reach their destination. However, there are a few people that are actually avoid the new path of finding another substitute path, and they keep waiting on the line or in the queue until the congestion is over. So although simple oblivious routing techniques make an inefficient use of the bandwidth available between the source and the destination, so routing techniques can also be classified based upon the method, which is actually a self decision or a centralized or a distributed routing. Centralized routing versus distributed routing, we have very good comments over here. There is an example over here. You can easily find this example in the book and you can try to solve this example. However, I will just giving you a brief introduction about the example. The examples of the deterministic routing algorithm includes the EQ or dimension order routing used in the mesh and a torus multi-computer network, and the ZOR routing in the hypercube. The following example illustrates the use of the deterministic routing technique in a hypercube network. Just what you need to do before solving this problem, you need to study about something related to the mesh and the torus multi-computer networks, and then you will have to find what is actually a hypercube. I am not going to disclose and discuss the hypercube and the mesh and the torus multi-computer over here, but they have actually explained it in the example over here, and they have discussed it as well. So then they actually find the route by which from origination to the destination. Now going towards the section 5.2.1, which is actually routing for broadcasting and multicasting. Now this concept has to be understood by you in a sense that if you are talking about the multicasting, as I have discussed in earlier in the class, that it's actually related to 10 people among the 22 listeners of a class. So if we have a number of 22 students in a class, and only I'm saying a message to those who are actually the failure students, that you will not receive the marks for your assignment actually you have copied. So that's why I'm talking to a network or sending a message to a multicast network. So only those who are actually got the receipt of being failed in the exam, so they might get notified by this. And if we talking about in comparison or in contrast, if we talk about the broadcast network, and this way you are actually talking to the people or the crowd all. So if you are sending a message in your WhatsApp on your group, and you're putting some @ sign with some name, so it simply means that you are putting the finger of those people 1, 2, 3, 4. If it is one, then you can say it's a unicast. If it is more than one, you can say it's a multicast. And if it is @ all, so it does mean you are sending message to the all recipients, those who are alive or dead, whatever, but they are your reachable ports or reachable nodes. So they are called to be as a broadcast. So if I'm telling you an example, if a company establish a cache network from its device, from its memory to the number of the processors, so only 2 processors are addressed for such a part of the memory. That's a multicast. And if the memory has to be connected with all the available processors, it's a broadcast. So whenever the memory is executing something or processing something, storing the attributes in it, so if they have to inform or notify all the processes. So it's a broadcast way. This session is going to be end after 10 minutes, so we are probably going on a break. The next topic we are going to discuss is about the routing potential problems. A number of possible problems can result from use of certain routing mechanism in the machine message passing system. These include deadlock, live lock, and starvation, which are explained below. We have already discussed this in the class as well, that deadlock is actually a, a, a process is requesting a memory or a resource which is actually held by another processor. Like P1 is requesting a memory M1. However, the Q1 is actually holding the M1, and Q1 is also asking another memory which is M2, and that M2 is allocated with P1. So that's a cross combination. It's a similar like every person is coming on a signal, 4-sided signal or a cross signal, and they wants to go and pass by. So there is a deadlock that neither P1 nor Q1 want to release the memory, so that if one of them can release the memory, the other can get it and resolute it process, and then the rest of the processor will process the instruction from it. So when two messages each hold the resources required by each other in order to move, both messages will be blocked. This is called a deadlock. It is a phenomena that occurs whenever there exists a cyclic dependency for resources. Remember this word, deadlock comes when there is a cyclic dependencies. So I need you and you need another one, and they need me. So there comes a cycle. So until any one of us can drop its redundancy, so that can bring us to work. So there are many methods to overcome the deadlocks as well. So more common techniques to avoid the occurrences of deadlock is it can be achieved by ordering the network resources and requiring the messages. So actually we need to have an order of the request by which we can say, okay, P1 is a higher priority, P1 is scheduled as a high, or P1 is currently executing this thing, so no other process can use this thing, which is actually a mutual exclusion sort of a problem. So the channel dependency graph is actually a CDG. It's a technique used to develop a deadlock-free routing algorithm. A CDG is directed graph. Again, okay, it's a directed graph. So directed graph means that every vector has some certain directions by which they can mark from one position to another position and from one node to another node, which has to be written in a way like D is equals to G of C of E, where C is actually the vertex set and E is the edges includer. So every time when we would like to develop a graph by a D, so we must have something which is actually the graph of C and E all together connected. I'm really sorry, a little bit having cough. So consider an example of the 4 nodes network shown in the figure 5.4a. So this figure 5.4a. So that's a cyclic dependency among each other. So every node has is depending upon other node, and they are actually one cycle is over here. And okay, if this is only the single problem, we might resolve it, but there is another problem which is actually an inverse dependency as well. So that can create a problem for us. So if we resolve it like C1, C2, C2, C3, C4, there is a two chains altogether, which is C1, C2, C3, C4. And in another chain, there is another cycle, which is C5, C6, C7, and C8. So the static injection model result when all the nodes injected their messages at the same moment. The network clear of messages, what happens that they need to actually clear all the messages, remove all the dependencies, and then ask all the processors to send the messages one by one based upon some priority. This is to be compared with a dynamic injection, according to which the node can inject their messages at an arbitrary times. So there must be some arbitrary unit which has to be associated among them, and the arbitrary unit is responsible to keep the message and keep the record of the message, uh, and let the system knows that which message is passed before which one. So there is no deadlock can occur. So live lock can take place in a dynamic injection problem. It can occur if a static injection is used. A number of routing policies can be seen over here, be used to avoid the live lock. They are based on the following. Let S be the set of priorities that is totally ordered. Again, if you are announcing the priority, there comes a process problem that simply if there is an interrupt is occurring and there are some running processes altogether. So we say earlier that okay, interrupts are prioritized then over a running execution process. So we actually halt those running processes and we continue uh, with the interrupts process. And that's the second state. The third state is the starvation. We have already discussed it in the class, that what is actually the starvation. We have discussed the some issues related to the food starvation and as an example. And over here the starvation is a node is said to suffer from starvation if it is if it has a message to inject into the network. Injection of the network it simply means sending a message on the network, but it is never allowed to do so. So it is keep waiting, waiting. Like if you are waiting for your results and you keep waiting until you find that okay, it's the process of waiting becomes so long, we can call this as starvation. Starvation cannot arise if a static injection is used. Okay, so we know that if a static injection, we know which processor has which message to be passed. So there is no possibility that there is starvation occur. The simplest among them is to allow each node is to have the injection queue. Okay, how actually it occurs? A number of the routing policies can be used in order to avoid the starvation taking, and the simplest one of the simplest is to allow each node allow. Let me mark over here, allow each node to have its injection. So P1 is injecting, P2 is injection, P3 injection, and we just need to have a queue. So the most important thing is to remain all the processes intact and without starvation. We need to generate an injection queue so that we have a queue, and then based upon the queue we can implement this thing. As long as a fair queue management policy is used, this method prevents starvation from happening. It's similar like you are not going to wait so long to come into the power, so or to inject your message. So the third point, which is actually the 5.3 section, we will discuss it after a break.